fraction of that overlap that we essentially see. And that F score is basically a distribution of that overlap. And if the overlap is large, it's basically likely non-significant. If it's small, then it's more likely significant. This data is then aggregated in a so-called source table. So we have a source table that basically comprises of 4 different components. One is the sum of squares, so the sum of squares between and the sum of squares within, summed up to the sum of squares total. There's freedom because freedom between and within, and summed up to total. Based on these 2 columns, we calculate the variance between and the variance within, and that will allow us to calculate our F score. So this is probably any questions to that? I think we discussed it. I think it's clear. So if we're looking now at our society example, remember that dictator game, where basically members of different societies were asked to play the so-called dictator game. We had a null hypothesis that all 4 groups are different, and a research hypothesis that at least one of those is different. We are then calculating these 3 sum of squares. We have first step, we are bringing this data from a wide format into a long format. Then basically calculating group means. Important is that degrees of freedom need to be preserved. So we're arranging it in a way that each of these entries does have a group mean entry. We are then showing the deviation between that gives us an estimate of the sum of squares or the square deviations from the grand mean. So that's basically the individual group mean minus the grand mean, which is that black arrow on my graph. So you get deviations for each entry, which is consistent with group mean because it's just subtracting a constant. But it's important to calculate that because that gives you an estimate of the sum of squares between. So that's just the sum of these squared deviations. Next, we're calculating the within variability, which is basically the deviation of the individual score from the mean. Squared gets you for each entry a squared deviation. Summing that up basically gives you then a sum of squares within. We're getting then, lastly, we're getting a sum of square total, which is basically a deviation total of each individual score from the grand mean squared. And that basically allows the summing, the total sum. Yes, and this you enter in your ANOVA source table, which is basically between and within. The sum of these 2 is basically adding up to the total sum of squares. It has an arithmetic dependencies between these 3. We're taking then the degrees of freedom 3 and 9. That's up to 12. And we can calculate based on that, we can calculate the variance. And based on these 2 variances, we can calculate the F. So that's how we did it for the between groups, right? We did then in the last step, we did the calculation of the R squared, where the R squared is basically the between group sum of squares divided by the total sum of squares. Gets you an idea of the effect size. So we're looking at the within groups variability, and this is the beer drinker example. Well, basically, we have scores here ratings for each of the participants, for each different beer. We have brought it from a wide format into a long format. We have basically then calculated means, which is basically the mean of these beer type ratings. We have then lastly taken the subject mean, which is basically the mean for each subject individually. So subject 1 has 40, 30, and 53. So it didn't like the mid-range field, only like the cheap field. So basically we're calculating a mean for each subject. That allows us to depict that variability. So now these basically lead then to the quantification of these total deviations, which is the individual score minus the grand mean squared. For each entry, sums up to sum of squares totally. We have then a mean minus a grand mean squared, which is basically getting us the sum of squares between. We're calculating lastly sum of squares between. We're calculating lastly the mean of a participant minus the grand mean squared, which is basically the deviation, the squared deviation from the subject mean. Bless you, bless you. Of each individual entry to preserve the degrees of freedom. You're summing that up, you get a sum of squares subject. Subtracting the sum of squares total minus the sum of squares subject is basic sum of squares total minus sum of squares between, and sum of squares subject gets you to the sum of squares within, which basically allows you then to estimate. And the reason why you have to do that is because when you think of an individual, so you're interested in the between groups variability and the true within groups variability. So the within groups variability, both the within groups and the between groups variability is to some extent dependent on the individual's preferences for that particular beer, right? So people have different taste preferences. They like different beers, they like different tastes. So you need to account for that to some extent, and you're doing that by subtracting the total variability, because that's the absolute truth. You know all the ratings, and you know what that grand mean is. That's your absolute truth. You know what the means are. You know what the variation of the means are. If you subtract this, what's left is basically all that's within, something that happens within all those groupings with all the participants. So now you have a certain variability that is attributed to the subject and to that subject's individual preferences. And you're removing that, and then you're left with the true within variability, not having to deal with the variability caused by the subject differences. That's the idea of within groups and over. And this is a superior test. If you have the opportunity in your research to have the same individual go through each stage of your intervention all the time, you have a purer group comparison of your intervention stages, because each subject thereby serves as his or her own control. So the difference from one stage to another stage is actually purely attributed to the difference between the groups. And the subject-specific uncertainty is being removed. That is really the trick with this. This is why it's scientifically actually very elegant to do that. It's just very hard to do, particularly when you study mortality, for obvious reasons. So good. So we are taking then this data and putting them in an ANOVA source table. The ANOVA source table looks pretty much the same as it does for the between groups ANOVA. We have between groups, within groups, subject, sum of squares, and the total sum of squares, same outline. Always note that the degrees of freedom are here basically amended or added the additional information of the subject degrees of freedom. The sum basically is beyond as the sum of these 3 degrees of freedom. We have then the variance for between groups, within groups, and subjects. And that gets us to two different Fs for our actually statistical testing. We only need the first F, so the between groups over within groups variance F. So that's briefly the calculations that we have done. So you remember that it was quite laborious, right? So there's quite a lot of calculation involved. So today we're going to do this in R, and we're going to play around with the codes that will allow you to do this a little faster. So please open your script. It's practice lab 4 solution. It's on Canvas. Load it into your R Studio. You're basically looking at the first 2 lines basically only serve to clear the environment. So this is the standard code that's always in there. You just select the first 2 lines, or you just click into the line. You don't even have to select it. You press Control and Enter, and it clears your entire environment. Yes.
What's the instructions, like the STAT1021G instructions? Anybody else? What's it called, the solution?
Yeah, you need an R code. Yeah. So the R code is then to be loaded into our Studio. And on line 5 and 6, you have a new code. And in case it's on your end not add a hashtag, please add the hashtag from it. And you remember that the hashtag basically comments out. That means it inactivates the function after it. So when you do install packages, you're basically installing that package. And we need those 2 packages in the following in line 7 and 8. We're calling these 2 packages, and we're actually activating them in the environment. With line 5 and 6, you're installing the packages. If you comment it out, it's inactivated and nothing happens. So if you just run this line, nothing happens. It's just starting at line 7. What you need to do after you have commented this out, you just select everything up until the hashtag, but leave the hashtag white. You don't select. The reason is because now you're only selecting the active portion of it, and now we want to run it. And if you run it, you press Control and Return, and then something like that will happen. You just say yes. You just restart it, and now it will install your packages. And that's when all this craziness happens down there. Just forget about it. R is doing this all itself. You don't need to do anything, and it's basically just installing the packages. That just looks more complicated than it actually is. Please do this for all 2 packages, R statics and dplyr. Yeah, it takes a while. Don't worry about it. Yes.
For some reason, mine keeps on just jumping to line 20.
Line 20.
Yeah,
That's not possible.
it's Control V, right?
Control Enter. Or Control Return.
Thank you.
Okay, once this happened, please go in line 7 and line 8 and just load and activate these 2 packages. That should take seconds. Next, we go into line 12 and 13. With 12 and 13, and we remember that from previous practice labs, data.frame basically creates a data frame that will allow essentially to create 2 different variables. And that is for our dictator game example. exactly the data we needed to do our analysis. So we have society and score here lined up. Once we have run that, we can go on line 15. Line 15 basically activates the same data frame. Basically, we have cheap, mid-range, and high-end beer lined up just in the same fashion with the participant ID basically here on the left column.
Why don't you accept?
7 and 8. Yeah, we run 7 and 8 too. Control and return. Yeah. Good. So since we loaded the dplyr package, dplyr is actually a wonderful package that allows us with group by to split our and add a grouping to our data frame 1. And we're telling it in the first part, so group by in parentheses, EF1 is the data frame of interest. And then we have society, that's our actual grouping factor. And it allows then in the following to use it as a so-called pipe. This is a so-called pipe. So those of you who will do some computer programming, that's quite a useful function. The people have quite back. This pipe basically moves this data in that format grouped as per that society factor into the function summarize. And summarize basically gives you a count, a mean, and a standard deviation. So that's how simple it is. So dplyr, I highly recommend dplyr, very fun package, very useful. So if we're doing this now with our society example, our dictator again, we're basically getting 4 different levels, 4 different. We're getting the counts, we're getting the means, we're getting the standard. Equally, if we do the same thing with line 26, we do the same thing. 26 to 30 does the same thing. Data frame 2 groups it by the beer type, summarizes it with the count with the mean and standard. Basically gets you cheap, high-end, and mid-range. Gives you the estimates for the beer. It was 5 ratings with a mean for each beer type. The standard deviation was a mean beer type. So here with group by on line 32 to 36, we changed a little bit the grouping factor. So we have data frame 2 as a function of participants. The grouping factor here is participants. With the pipe again, going to summarize with count, means, and standard. So now we get a mean and the count and the standard deviation for each participant. So these are the means for the participants. So these are consistent with those means that we calculated here in our spreadsheet. It's basically a little faster. So this is basically how you build that. You can also, you have different commands. So if you go back up and you go here at the end of df1, you can do summary df1. And that's also, that's maybe quite useful to know. Whenever you do summary, if you have an object loaded in some shape or form, you want to see what that object looks like. With summary and the object after, you basically always get a good overview what that object contains. So here you have for society, you have 3, 4, 5, 3 entries. You get a score. With the score, you always get a min, max, first, third, quartile, which is 27th, 25th to 75th percentile. You get a median and a mean. Based on that median and the mean, do you think that the data is considerably normally distributed? Yeah, no, yeah, yes, why?
Like 40 and 39. 34.
Exactly. In a perfect, very good. In a perfect normal distribution, mean, median, and mode is identical. Right? Remember that. If there were an outlier in your data, which one would move first? One outlier. One value that's a little higher than the other ones. Which one starts moving first? Which one gets affected stronger? Mean, median, or mode? Why?
You ask them all and divide it. So there's one that
Exactly. Because of the arithmetic dependency, the mean needs to move right away, whereas the median is basically splitting the data in half, right? Very good, thank you. The median does nothing else but splitting the data in half, so it's basically the middle score. So if you basically you have here big data scores somewhere on the range between 28 to 52, and you have your mean right somewhere in the middle of 40, and then suddenly one of the players is like super fair and like gets 100%. The mean has to arithmetically shift. The median is not going to care. The middle score is still where it is, and leave alone the modes. That modes doesn't move at all. Well, it moves eventually, but not right away. Okay. So that's the summary, and the summary is useful to do because it also gives you an idea of the distribution. It also gives you an idea of how does the data look like, what type of data is it. That can also be done with a command called strdf1, for example, gives you here an overview. What does this data actually contain and what's the nature of it? So if you have strdf1, you get certain observation of two variables. You get the respective variables, you get society and score, what society is affected with score levels. You get score, you get a numeric value that basically distributes around the mean of 40. If you do the same with the F2, you basically get the same thing. You get 15 observation over 3 variables. You get participant integer numbers. You get peer types. It's factor with 3 levels, cheap, high, and mid range. And you get a rating that is numeric. So we did the descriptive stats. We know how to get this descriptive stats, and these are the descriptive stats that you're basically comparing to each other, right? So you are interested in your group means, you are interested to actually what are the central tendency markers of these. So if you want to essentially analyze this now as an ANOVA, you have basically, so there are various ANOVA functions in R that you could utilize for that. One of them is AOV. So AOV is actually part of the base package. So you have these packages that we just loaded. These are additional packages that are being activated in R, which come with additional functions. Again, and this is the beauty of R, and this is where R is an advantage to other commercially available statistical softwares, because you have access to functions, to packages, to advanced analytic methods that have been developed anywhere in the world. If somebody wrote a PhD thesis in mathematics or in statistics in Singapore, and then puts it out there and publishes it for free, which most statisticians and developers do, you have that at your disposition the next day after you defended this thesis, and you can utilize it for your work. So this is a perfect example of open science. So you remember we talked about open science, open data, open research, and transparency. So you basically, with open coding, you have the next level essentially. So you virtually have the opportunity on a platform like, for example, GitHub, to really go into the code repositories of real experts in the field that have it made public to the community. And that's actually a very useful tool, and it's a very helpful community. It's a very helpful community that are very open about their work, and they share codes freely between each other. To some extent, they also like to brag about their code. So it's a very fluctuating and very helpful community. So GitHub, those of you that go into the realm of computer science, is like definitely get yourself an account there and just make sure that you share your work. In the same context, I also want to show also Stack Overflow. The next beauty that is, so if you have a software like SPSS or you have SAS or I don't know whatever software you want to use, when you have a problem, you have to go into the help menu, right? So in the help menu, you're going to find your answer or not. If worse comes to worse, you're going to contact SAS and you're going to tell them, hey, I have a problem, I need help. And then 3 weeks later, somebody comes back and it's probably fast. SAS is too expensive to not be faster. But essentially, so you get support, yeah, in a different way and fashion. With R, you don't have support. There's no support. So there are some central repositories that are basically maintained, but it's all non-profit. That's why everything is for free. However, what is literally priceless, and there cannot be a price tag on it, is for like Stack Overflow. Well, whenever you're coding something, you have a problem, you will find a solution there. I think altogether I have like maybe over my entire time doing research and doing R coding, I may have like 4 or 5 examples of things that I wasn't able to locate a solution for in there. All the other things you find within minutes, seconds. You type in your problem. Well, let's bring it to the test. Let's say, let's take out the n_r.rm equals true, because there are missing values in there. We know that. So when I run this now, I do not get a missing value. Let's find one with a missing value. What is missing value is df1. Okay, df1 213. Let's make this an A. Okay. Okay, so now we have, if I do now summary, to SD df1 score, I get an error 1. Okay, let's take this with error warning then. Okay, so you take this error warning and you go on Stack Overflow. You have here search. Robert. You get here search results, where basically somebody posted the same problem and somebody else commented on it and gave you an answer. And then you can rate the answers, and the administrator on the other, they're also doing this for free. This is all non-profit, this is all for free. Administrators on the other link these comments together, kick out those that are not good answers, and basically rank the answers according to the beauty of the solution. So that's Stack Overflow. It's very useful. Okay, let's go back to that. So yeah, so GitHub, Stack Overflow. So there are different functions, different codes for different problems. For the between groups ANOVA, we can go with the simple version of AOV. So that's ANOVA in base R. That's a very simple code. We basically were saying AOV, so we're packing it here in the package ANOVA1. We're using the function AOV. We're using the variable score, determining this as the dependent variable, followed by a mathematical tilde, which basically is then followed by the independent variable. So we're analyzing score as a function of independent variables society, and we say that the data comes from DF1. If we're running this, we basically have now a new object here on the right, which is ANOVA1, which basically, if we click on it, and there's a magnifying glass right next to it, we can look at the various things that are contained in our ANOVA1 object, where we are only interested in a few. But more about that later. So there are a lot of things that basically are not useful and not necessary to understand right now. But let's focus just on summary. Because if you do summary and your ANOVA object, you're basically getting that ANOVA source table that basically will allow you now to, no, that's the wrong one. You get that ANOVA source table that basically allows you now to do your hypothesis testing. So as said, the ANOVA source table, it's crucial that you understand what components are in a source table and how does it look like. It looks different between different softwares. R gives you, there's a border like that. It's always the same out there. So basically you get society as the independent variable, that's your between groups, some of them. Then you get residuals, and residuals are basically your individual points and how they're dealing. So that's your within groups. The degrees of freedom we know are 3 and 9. It doesn't give you a total because you don't actually need the total. That's just the extra mile you want to go. Then you get a mean squared, which is the MS, that's your variance. So it's the mean squared deviations. The variance by definition is nothing else but the mean squared deviation. So you take the sum of squares, you divide it by the degrees of freedom, you get that mean squared, you get your variance. That's basically 153.9 and 18.6. And you get the corresponding F value, F score. And that is automatically, again, I have mentioned it before. This is basically each of these blocks is showing you a function of that F distribution for that respective characteristic degrees of freedom in the denominator and degrees of freedom in the numerator. R is not using an F score table. Logically, R is basically taking the mathematical formula, the mathematical function to determine how much area under the curve is after that F score. So if I have an F score of 8.27, that's somewhere here, it calculates exactly how much area under the curve is beyond this F score. And that is the p-value that is reported in R. So it gives you an exact estimate of that p-value, which the critical value indicates 5%. If it's further in, it's smaller than 5%. So that means that we have a significant difference between at least two groups. So in one comparison, there's a significant difference. So this being said, we would like to understand which one. And that can be done, as we know, with post hoc tests. And we have here on 49 and 50, we have two post hoc tests. We have our Taki on a significant difference test, and we have a Bonferroni pairwise t-test. The Taki, let's start off with the Taki. So if we run line 49, we're basically getting the Taki, and that essentially does a pairwise comparison with a 95% confidence. It gives you a comparison between foraging and farming, industrial and farming, natural resource farming, and foraging. So it gives you these differences These are the differences between the means with the 95% confidence. As we know, as soon as both interval limits, boundaries, are either positive or negative, this is a significant difference at an alpha level of 5%, right? Remember that, in confidence. And this is corresponding with the p-values that we're getting. So now keep in mind, this is p adjusted. If you remember from the post hoc testing that we did was the between groups ANOVA. TACI is calculated as mean 1 minus mean 2 divided by our standard error of the mean, which is calculated as the variance divided by the sample size square root. So that's our standard error of the mean. So this is essentially a standard hypothesis test. And then this derived Q is then compared to the Q table. And this gives you the actual p-value. However, R has basically transformed this into a p-value. So both of these, all these three comparisons are basically significant because it's smaller than 0.05. So that can, from a TACI, you can just read that exactly with that interpretation. So this p adjusted basically reflects an adjusted p-value adjusted for multiple comparisons and penalized for these multiple comparisons and the associated inflated type 1 error risk. So line 50 is a pairwise t-test. There's a pairwise t-test using a Bonferroni. Remember, Bonferroni adjusts the p-value by dividing it by the number of comparisons. So you have an adjusted p-value that is now penalized for the multiple comparisons that you have conducted. And you're interpreting it in the same fashion as TACI has done. You have columns, you have the rows, follow the column, and where it meets the row, this is the corresponding p-value. So farming versus industrial gives you a p-value of 18.5%. Foraging versus industrial gives you 5.9%. So this is not significant. And it's interesting to see because here you only have three significant levels. Three significant comparisons. Whereas here with TACI, we had two. Here only two, whereas TACI had three. Why is that? Because one test is stricter than the other. And Bonferroni just is stricter as the TACI. And well, I have never done a TACI in the real world, but I would gravitate always towards Bonferroni. Because like you can read up on the reasons. I'm not 100% certain what the reasons are, but it's stricter. Yes, no, but it's so there may be reasons. Actually, I put in my to-do list to read up over the weekend. I'll keep you posted. Good. So that was the between groups. Simple, right? Simple, 3 lines, you're done and overdone. If you have now within groups, so we have arranged our DF2, that's our beer drinker example. If you run now line 44, takes a little longer. We're building ANOVA 2. ANOVA 2 is now an object containing ANOVA test. Looks a little different. Not giving me what I hoped I could give you. So ANOVA test is a different, and this is why we loaded the rstatics package, because it gives you different functions. ANOVA underlying test. In ANOVA test, you define the container variable, the within groups variable, participant ID, data. So you're identifying what is the participant ID. And with get ANOVA table, you're basically getting the ANOVA table, as the name implies. So you're basically looking at the same data that you have in your module 17 spreadsheet. basically corresponds with exactly the same. So it gives it a little bit collapsed and then in a simpler format. So you basically have 2 degrees of freedom. That only gives you between groups, gives you 2 degrees of freedom. It gives you degrees of freedom within in the second column. It gives you a corresponding F and it gives you a corresponding P. And that P is the ANOVA P value. So that's tested against the F distribution. Then it also gives you P total. This is a different P than that you will not need at this point, because that essentially indicates it is of low predictive accuracy. So it doesn't give you much prediction power. So ANOVA and regression are kind of overlapping to some extent. So that means they are to some extent intertwining in the approach. So ANOVA does also use the R square, which comes back with the prediction in the regression. So this is basically something for chapter 16. Yeah, so this is the get ANOVA test. Get the ANOVA test from the R statics package. And then we can also do with the same approach, we can use a POST test now. So basically comparing response by one correction, same comparison. So we have now no significant difference between cheap and high end here. It's like borderline significant, 5.7%. So we do have a significant difference between mid-range and high end here, 1.5%, and no difference between cheap and mid-range beer. So that's basically what we want to test. Any questions? Okay. All right. So once you have done this, and you have the code completed, you click on the console, you press Control and L. You click on the script, you press Command and A, and you press Control and Return. That basically runs the entire script, and you have that entire script now in your console. Go at the end of your entire script, go after the I of Bonferroni, go all the way up until you're back at clear the environment. Press Command and C, go on the spotlight, look for a text edit, open a text edit file, open new document, press Command and V, and save that file into your folder, basically as a STAT1021G, practice lab 4, and your family name. Save this and submit this via Canvas. That's practice lab 4. You're welcome. So that's 10 points. So it's a low hanging fruit. No, but I think it's important that you have seen it and you have it somewhere at your disposition. I highly recommend to kind of try to get some familiarity with R. Those of you that are interested, reach out to me. We can dedicate some time over the holidays or anytime before or after the final. Yeah, that's pretty much all I had for today. Any questions? If not, then we can conclude and have a nice evening and happy holidays.
Like 5 minutes late, so did you see?
Leah.
Yeah. Thank you.
Oh, Mr. Raven, is there gonna be like homework throughout that we can complete throughout the break?
What was it?
Is there like homework that's gonna be throughout the break? I think I saw that. Like,
There's a homework due at one point in April.
Is it like within 2 weeks?
Well, whenever it's due, it's due. I don't know. I don't know by heart. When is it due?
No, we don't take time anyway, it's like, like a lot.
What is the question?
Yeah, there was one part in the homework.
Oh.
Thank you.
Sure. Yeah.
We're a couple minutes late.
I have that.
Good night.
Sure, you too.
Good night.
Good night. Thank you. Bye-bye.
You too.
Thank you, you too.